Looks like Good Noodle isn't here. It's possible that he didn't show up because I was a little late, so he might not have seen me. But
Oh, you might join.
we'll see.
I
He's normally pretty timely, so I. Oh, there we go.
think.
Okay, cool. How's it going, Good Noodle?
I'm good. How are you?
All right, I'm doing good. I was just a little concerned because you were 5 minutes late, but it's okay because so was I. So, anyways, doesn't matter. You guys got any questions for me? Or are we just sitting around a campfire having fun?
Yeah.
That second one?
Yeah, I'm up to talk about whatever Good Noodle needs.
You got any questions, Good Noodle?
Oh, yeah, I suppose. Because
Okay.
we just went over machine code
Yeah.
and how it turns into zeros and ones.
Yep.
When you compile it, and like if I were to compile high level code and then I would get the binary of it, right? Isn't that the machine code or is that something different?
Yeah, that's. So, yeah, it's mostly the machine code. That's primarily what you're going to get when you compile. Um, there are different files you get when you compile down stuff. So, right, when you compile, you then turn it into assembly. And then the assembly then becomes your machine code. But you also have to store the information for example, like including libraries and stuff. So you have a linker which links all of the files that you're compiling together and basically orders the machine code in a proper format. So that information is stored and generated as well. But at the very, very end, the only thing that actually goes to your CPU is the instructions. And the only thing that goes to your memory is the list of the instructions, kind of ordered in memory, and uh, any data that would go to your data memory. So, for example, if you're using constants, like if you used a constant uh, GPA equals 4.0, for example, that would be stored in your data memory, and that way, whenever you use that constant in your code, it would then access the data at that memory. And so there has to be something which tells you where to map those constants to memory. And so that's dealt with by your linker. And and some other stuff as well, but for the most part, yeah, the machine code's the only thing you really have to worry about.
I see. I was just asking this just because like when you try to access like a binary, it gives you like these weird symbols.
Yeah, that's just because it's a .bin file because it's binary. It's just straight binary, right? But when you try to open it, you need to remember that when you're trying to open it in your text editor is trying to interpret the binary file probably as like ASCII or something. And so then when it reads in those ASCII values, then the digits that get displayed or the characters that get displayed to you are going to be very, very randomized because the binary file, it's encoded in just pure binary, just zeros and ones, and to the text editor, there's no pattern there. So it just takes the first 8 bits, converts it to an ASCII character, and prints it on your screen. But those first 8 bits could be like the first 8 bits of your assembly instruction. And those first 8 bits, they can vary wildly. It could be, 10000011. Okay, now you have a question mark on your screen. Awesome. That really helps. So whenever you try and view something in your text editor, it doesn't work too well. You typically have to have a specific viewer or convert the binary to a readable format. Yeah. Yeah. So it does look pretty awful.
Okay, thank you.
Yep. Any other questions?
I don't think so. No.
Nothing. What? I guess we'll just have to talk about BJCs and MOSFETs.
Oh God.
No. Um,
What? Wait, Good Noodle said he's in 221, right?
are you in 221 Good Noodle?
For electrical?
Yeah.
I've never taken an electrical class yet.
Oh, really?
Wait.
Yeah.
CPE or EE?
I'm CPE, yeah.
Oh, you are
Yeah, that
CPE.
makes sense. I think I took my first E class at the same time I took CPE 200. So like right now is when I would be taking my first circuits class for you guys.
That's a lot to go through. I took EE last semester. EE 220. And then 221 in December.
Oh, okay. I was like, how did you do both? Yeah, over the summer.
Yeah. Summer was brutal, but we made it through.
Yep. Um. Well, I mean, I'm not really sure how much class content I can talk about really, because right now you guys are just doing machine code stuff, and you just look up a table and copy paste basically. But are there any other topics you guys want to review from anything we've gone over before?
Yeah. I just don't know.
That's very fair.
I'm gonna look through all the homework.
Sounds good.
So we're starting from, let me see, where the midterm is starting from. I'm so disorganized. Okay, so it's going to be through counters, memories, C programming. Do you think we'll actually on the midterm have any like program this into high level coding?
I doubt
But
it.
it'll be more like translate this from high level code to this. Okay. And then do you think
I will say that it's possible that you could be asked to generate high-level C code, like create it yourself, but likely the way that the problem's going to be is they're going to ask that, and then they're going to ask you to turn it into assembly, and then maybe like do machine code for one of the instructions or something. But that should be it.
so one more quick question. I don't know if you would know this. I can ask the professor, but the midterm isn't cumulative per se. Like
No, it's
so-
not cumulative.
Yeah, like
It-
System Verilog, that was last
So
time. So,
I'm pretty sure the way she does it is obviously foundational knowledge you still need to know, but the specific topics you'll be examined on, or that's going to be on your test, is the same stuff that you've been doing in the homework since the last midterm.
okay.
I believe that's the way she does it. So,
Yeah, because I don't think we had any. The System Verilog, I believe, was before the midterm. I don't think we've done any snippets since then. And that I feel like is my super one, but I don't want to review it now. I'd rather review something that's like for sure.
just so you know, System Verilog probably will be on your final.
Yes, so the final will have, I think, everything.
Yes.
So I definitely need to come back to that. But let's see. So linking and launching application system design. We haven't. Is linking? That's not like jump and link, right?
No, linking as in what I was describing earlier,
Okay.
when you have multiple C codes and you have to link them all together and
Okay.
things like that.
So yeah, I think we'll probably go over that next week. Yeah, it's 11:06. I don't know. Like Good Noodle, what do you want to like review, or if you want to talk about something new?
Oh, I should turn on my camera. Sorry. I did not even realize that it was off. Whoops. There we go. Now you can see me, right?
Yes.
Okay, good.
I was like, Victor will turn it on when he's ready.
No, I just forgot to turn it on.
So
I
it's
mean-
homework. It looks like it's homework 8 through 18.
Okay.
Which 17 is due Monday, and then 18 will be due Wednesday,
When's your guys' midterm?
the following Thursday, or following Wednesday. So I keep saying Thursday.
So not next week, but the week after, yeah?
Yes, correct. Yeah, it's on 11/15.
And you guys don't have any homework due on not this upcoming Monday, but the next Monday, because that's your midterm review?
Right. Yeah, no homework due 11/13.
Okay.
So yeah, we just haven't. The only thing we haven't learned is the linking and launching applications, system design. Well, the rest is sequential building blocks, counters memory, C programming, counters, RISC instructions, including branch, conditional, loops, arrays, function calls, the stack, recursion, machine instructions. So those are our topics.
What do you guys go about after the midterm?
After the midterm is combinational building blocks, carry look-ahead errors, and then shift. Oh, the shift registers, which you were just talking about. I was wondering, like, if we were going to learn that. Logical arrays, PLAs, and FPGAs, parallelism, microarchitecture, and that is it.
Okay.
There's only 2 weeks of material after the midterm.
Yeah, that sounds about right.
So yeah, I don't know. You know, do you have anything like you're
Dying to go
worried
over.
about, or like, yeah?
I don't think so. I mean, I feel as though we just gotta like rework the previous problems, and then I think it should be good. Because I for sure have forgotten like the adder, the comparator, and then like the flags. I need to make sure that I remember how to do that because that might be on that for sure
I
might
mean,
be
if
on
you
the
want
test.
to look, you said starting at homework 8?
Yeah, homework 8 was the one due right after our midterm, and it does have system Verilog, particularly a multiplexer in system Verilog with combination logic, and then a parameterize module, which I forgot all about the parameterize stuff.
That's very fair. So yeah, I'll tell you what, you can take a look through your homework starting from 8, and if you see any questions, either tell me or start writing them down and we can go through them, whatever order y'all want.
Okay, I do have a question then.
Yep.
Can we review, not necessarily the calculations, but like the idea behind, like the counters and dividing the clock? Like specifically these kinds of questions where we've got,
Yeah, we can talk about those.
like more of like what's like actually happening.
All right, what colors do you guys think a clock is? That's going to determine.
Black, because
Black?
sometimes it's hard to see the other colors.
What do you think, Good Noodle? What color is a clock?
We can go with black, yeah.
Black? All right. Okay. So, recall that a counter looks like a register with a adder at the front. So it'll look like this. And then this number 1 here can be any number. It doesn't have to be 1. Typically, you call it M for multiplier, or I think in the notes it was called P or something. And so our job is to ask what kind of clock we get out of this system. So, for example, we supply a clock to this register, and here's exactly what happens. So I have my clock signal, call it CLK, and we have to ask ourselves what happens as this clock signal progresses to my register. So the register starts with an initial value of 0. Let's just say that we had a resettable flip-flop and that we were running this on a test bench, and we pulse the reset signal, and then now we're measuring what happens right after. And just to make my life easier, let's say that it is 1 here on the entrance of the counter, or on the entrance of the on the input of the adder. And so here's what happens. We're waiting on the clock to strike, and while we're waiting, we can say a little bit of information about our output. I'm going to call it Q when I write it up here, but that's also just the count of the number stored in the register. So it could be count bit 0, count bit 1, count bit 2, etc. We know that initially, because we pulsed the reset, that all of these are at zeros. However, once we have that clock, that rising edge of the clock hit, we read in the value from this output of the adder into my register. And so again, what that's going to do is we notice that the output of this register was originally 0. 0 plus 1 is 1, so it's going to read in a 1. So now the input of the register is going to be 1. Or sorry, the input of the register is going to be run, and the register is going to store the value 1. And so what that means is that whatever the binary encoding is for this, however many bits it is, it's going to look something like this now. A bunch of leading zeros with a 1 at the end. Where this is the least significant bit, Q bit 0, Q bit 1, Q bit 2, etc. So we just said this went up to a 1, which means that Q bit 0 has just gone up to a 1. Whereas the rest of my bits remain zeros. Until the next rising edge of my clock, which occurs here. At this next stage, we have 1 in the register being added with 1 on the other input of my adder. And when I add them together, I get 2, and that's the next value that's going to be stored into my register. So now, this is what I'm going to be storing. All I did was I wrote the binary encoding for 2, the binary representation of 2, and here you'll notice that this bottom bit Q, has actually gone back down to 0. But our next least significant bit has gone up to 1. And our next least significant bit, Q bit 2, is still 0. And so this pattern is just going to keep repeating itself, where we're essentially counting in binary. And so we know that every single clock edge, every single rising clock edge, Q0 is just going to go up, down, up, down. So what that means is it started low. At the next clock edge, it's going to go high. Then it went low. Now it's going to go high again. And then it's going to go low at the next clock edge. And then it's going to go high at the next clock edge. And I'll go ahead and just write out these bits to make my life easier. And I'll write them all out. 0, 0, 0, 1, 0, 0. So I'm reading where the bottom bit is the most significant, so it's a little backwards, but this is the number 0, this is the number 1. The next one is going to be the number 2. And then the number 3. So that means this is going to stay on, this is going to be low. And then my next number is going to be 4. Yeah. Let's do that. So that's my number 4, where this goes back down. Oops. This goes back down. And this goes up. And so we continue counting, and this is the exact progression we're going to see throughout all of our bits. And so the important part that we see is the following. We know that we have a clock period for this given clock. So let's say it was a 1 gigahertz. Let's say it was a 1 gigahertz clock. Another way of representing this number is in terms of its period. So instead of its frequency, which is this, frequency of the clock, we can say the period of the clock, t, is 1 over that, 1 over 1 gigahertz, which is 1 nanosecond. So we know that this distance here, this period, for my original clock was 1 nanosecond. Now what that means for the rest of my information is I can do the following. I know that it takes 2 full clock cycles for Q0 to do its own full cycle, to go up and then all the way back down. Therefore, its clock period, or its period, is double the original clock period, which would be 2 nanoseconds. The clock period for Q1 is going to be 1, 2, 3, 4 clock cycles before it heads back down to 0. So that's this entire distance right here. And that's 4 nanoseconds. And you can't see it now, but it's going to be for Q2, it's going to be low for 4 clock cycles and then high for 4 more clock cycles. So it's going to be a total period of 8 nanoseconds. And in general, this pattern of powers of 2 repeats. 1, 2, 4, 8. The next bit would be 16, 32, 64, etc. And so since our period is doubling, every time our frequency gets cut in half. So for example, if our period for Q bit 0 is equal to 2 nanoseconds, like we said it was up in the description, we know that up in the diagram, we know that the frequency is equal to 1 over 2 nanoseconds, which is half of a gigahertz. That's my frequency. And so you'll notice that frequency has been halved, or cut in half. And every time you go down, you cut the frequency in half over and over and over again. So in other words, if you have a very, very fast clock, you can derive a much slower clock that's still synchronous to this one. And when I say synchronous, I mean that edges on the derived clock align with edges from the original clock. So for example, on this guy, qubit 1, that edge aligns with one of the clock edges, and this edge also aligns with one of the clock edges. So they're synchronous. One's derived from the other.
A second clock?
We can treat these as clock sources if we send them to other bits of logic. All I'm saying is that it's periodic, and it's periodic specifically with respect to the original clock. It's derived from that original clock. And so they're synchronized in that way, in that sense. And so now I can develop an arbitrarily slow clock, as slow as I want to go. I don't have to go down to just like 1 hertz. I can go slower than that. I can make it so it's in millihertz or something stupid. Something very, very slow. This is very helpful for if you want to, for example, read the inputs from a water bottle to measure its water level. This is how you generate that slower clock. And then you can pick your bit depending on how slow you want to go. if I wanted this to go all the way down to 1 hertz, I would need, I'd need probably, I think, like 26 bits. I may be remembering incorrectly. But in general, the formula is the new frequency you get is equal to the old frequency of the clock over 2 to the n plus 1. So for example, in the n equals 0 case, that refers to qubit 0. We plug in 0, and we get 2 to the 1. So you're cutting it in half, which is what we said happened. If you're referring to qubit 1, you plug in 2 to the 1 plus 1, 2 squared, so you're dividing it by 4, which is indeed what we did. We divided it by 4, or we quadrupled the period. And so this holds for all of my bits. And if I wanted a clock that was, say, 1 hertz, I would just have to figure out how many bits down I need to go until I get 1 gigahertz divided by something that's close to 1 billion. So whatever power I have to put here to get close to 1 billion, that's what I'd have to put. And that would be around 2 to the, I think it's like actually 2 to the 30, because 2 to the 30 is about 1 billion. So it'd be right around there. So if you had a 30-bit register and you took a look at bit 29, so if this was 30 bits, 30 bits, there, you'd say, okay, well now my count is, or my Q value is 29 to 0. And I want to take a look at the frequency of Q bit 29. Well, that frequency is going to be equal to the original frequency, 1 gigahertz, divided by 2 to the 29 plus 1, or 2 to the 30.
So then, do you like, in System Verilog, would you like set up another like flip-flop and then like say, like
You would
it
just make this a
gets
multi-bit.
that?
You would just make this a multi-bit register. That's all you do.
Okay.
Or are you saying like if I wanted to pick off the
Yes,
signal
if you wanted to pick off like the bit and then
and like send it to
use
the
that
output of
as
the
a
module?
clock.
Yeah, I mean, all you would do is you would just, in your port list, you would say, you would make a signal clock out, and then inside, so you'd say output, logic, clock out, and it's a 1-bit signal. Clocks are 1-bit signals. And then inside in the body of your code, you would, somewhere in there, you'd say something like assign clock out equal, and then you would just say qubit 29. Because you want that bit 29 to be the clock. So you just assign that to that wire, i.e. you run the wire outside of your module, and that's it. That's how you send the clock places.
Oh, okay. That makes sense. Seeing how it gets put together.
All right, so now I'm going to do 1 billion divided by 2 to the 30. 2 to the 30 is approximately 1 billion, so I should get a number a little bit less than 1 hertz here when I plug it in. Let's see what I got. A little bit less. 0.93. So that would be the frequency of my of qubit 29. And if I was concerned to know how many times, if I wanted to know the period, I would just then take the reciprocal of this value, 1 over 0.93. And that means the period is equal to 1.07 seconds. So that is to say every 1.07 seconds, that's when your clock hits.
Interesting. So you use this for your sensor to like take the take the signal based on this new clock that you set up?
That's correct.
Yeah. Okay, thank you. That was like, I knew how to calculate it, but I didn't really know what it was.
No worries.
What I would use it for. Or
Well, that's one. Anytime you want something that's at a slower rate, this is what you do. You make a clock divider.
Okay. So this is called like a clock divider.
Yeah, it's called a clock divider.
Oh.
Yep. Though more generally, this particular circuit is known as a counter.
It's the counter.
But in this particular application, since we're using it for a clock to generate a clock signal, we would then call it a clock divider. So it's both.
I don't suppose you could like do a clock multiplier, right? Because it's only dependent on how fast your clock goes, right? Can't like make it go faster.
Yeah. Not with digital, at least as far as I'm aware, not with digital logic. Analog stuff, you can do. I don't think they're ever called clock multipliers. Well, they might be called clock multipliers, but I know that I think they're called PLLs, phase locked loops, where if you have some input clock, you can get an output frequency higher than the input. I don't know how they work, I'm going to be honest with you, but I have heard of those kinds of things.
Wait, can I ask like a tangential question?
Go for it.
Like, what is my partner like says overclocking on his PC? Like,
So
what is
when you have a desktop or any computer, any system, the people who designed it typically leave a little bit of wiggle room in terms of how quickly you can run your clock, because they don't want to send out a system and then have some people it work fine for, and then other people who like live in harder parts of the world where now your technology is running a little bit slower. Now they can't use it because the clock's too fast, and you get hold time and
Right.
setup time constraints
you,
that are violated.
yes, you violate them, right?
Okay, and that happens just because of the temperature differences or just because voltage variation in your supply. So what those people do is the designers purposely limit the clock. So they say, theoretically, here's my 100% mark. This is the fastest I could possibly run my clock. I'm going to put it at 80% of that speed. And so what overclockers do is they push it up, 85, 86, 87%. And now the system's still running fine, and as long as they keep it cooled well enough, and they have to do lots of cooling if
With
you're
the
overclocking,
water,
with
like,
water
in
cooling, yeah.
the-
So that's why you can overclock a system.
So what happens when you get like over, like the limit?
What
Do you
happens
just start
when
getting
what happens when a
garbage?
setup time constraint
You
happens?
just get garbage. Right?
You get garbage. Nothing works.
So like I'm thinking about like gaming. I'm sorry, good Neil, I'm going off on a tangent. But, like if you were like playing a game and it like
Well, if you're
finally,
playing a game and
crash.
everything would crash, your entire desktop would probably
Oh.
crash if you were trying to overclock too hard.
Yeah. Okay. Interesting.
If you are like right on the precipice, it might not crash. You just might get like visual bugs on your screen, or some like certain systems might crash, but not your entire desktop. Sometimes you can overclock not only your CPU, but also your memory. So those are the RAM sticks, the sticks of RAM. They're called DIMMs. So you can overclock those as well. Speed those up. Same reasoning, same rationale. But if you run those too much, again, you'll start getting errors and crashing and stuff.
Really interesting. I was just curious.
Y'all are asking a lot of good questions. I had these same ones when I was learning too.
You hear it all the time, but like nobody really knows what it means.
Yeah.
They're just like, oh yeah, I'm making it run faster.
Clock go fast. Yeah.
Like, okay.
But how does that work, really?
Yeah, like, oh, there's a clock on
Yeah.
it. That's weird. Okay, so
Perfect.
getting back, there's something.
What's up, Good Noodle?
Oh, sorry. Did you type in 16 divided by 2 to the power of 30? Is that how you... Wait.
It was 1 billion divided
1
by-
gigahertz, so 1
Yeah.
billion.
Oh, that's 1 gigahertz. Oh, okay.
Yeah. That's not a 6, sorry. That's a 1G.
Yeah.
1G hertz.
Thank you.
Yep.
So
Yep.
when we say array in Risk, it really isn't like, I mean, okay, so you know, like how in C++ it's really just like an ordered set of data, like each with an index, but like when we're talking about Risk, it's just ordered by where it is in memory,
Yeah.
right? But it's not like actually linked together when we're trying to make an array in Risk in any way. It's just linked.
It's
by,
just
like, an
the fact that
offset.
they are contiguous in memory.
Contiguous,
Yeah.
Right? Okay.
Yeah. It just depends on how you implement the data structure. So, for example, you in CS, you would eventually learn about linked list in CS 202.
Yeah, we just learned about that today. Okay.
And
those are actually linked though with a
yeah,
pointer.
so what you'd have is you store something to memory, and that the things you're storing to memory are two particular things: whatever data it is you're trying to store, and then a pointer. That pointer is going to point to another address in your memory, and so that's going to be a real, like, effective link to wherever your next set of data is. So they're not contiguous. They don't have to be contiguous because there are pointers that point to where all of your memory is going to be located. So,
Wait, but that's not the Risk array, right?
what do you mean?
So I'm trying to like,
Because when you say array,
yeah.
array doesn't really mean anything.
I know, that's why I'm getting confused. Okay, because I was like looking at, for example, so like for the lab, you know, they say, oh, with the bubble sort, like write a 15 element array starting at this address.
Yeah.
So in my mind, I'm just like initializing a base address
Yeah.
and then just offsetting it by 4.
Yep.
And like storing the data in each, and that's my array.
Yeah.
Even though it's just like a contiguous set of data. I think I'm just getting confused about the wording because like in my mind I'm like, oh yeah, I'm making like a variable called array, and I'm like, it
Well, what
has an
is
index.
literally what is at the baseline? What is your array variable? It's a pointer.
Yeah.
It's the pointer to the place where your array is stored. That's what that array is. So when you actually
Yeah.
write that code, that's what it decompiles into in assembly, a pointer.
It's like, I need to stop thinking about it in like C++ because it like gets me like really confused. And I mean, we do have an index, and like that's our offset. And yeah, okay.
Shauna,
Yeah.
you said that you guys did linked list. Is that after you guys did recursion?
Yeah, we finished recursion
Oh, okay.
last class. Are you in 202 as well?
Yes.
Oh, okay. Are we in the same class with Jimmy?
No, I don't think so.
Oh, okay.
I have Dr. Jorge Fonseca.
Oh, okay, yeah. Yeah, you guys didn't do linked list yet? We like just started it today.
No, we just finished recursion.
Okay. Yeah, you'll probably go through it tomorrow or whenever you have class. Yeah, actually, my professor said he's ahead a little bit, and I think he said generally you go over like linked lists after the midterm, which is next Thursday, because it's not on this midterm.
Hmm.
So, yeah. But it's just like a series of like chained like pointers pointing at each other. It's a linked list.
It's a link.
It is indeed a
That's
linked
what
list.
Jimmy said.
Yeah.
He's like, maybe I can just say it's a linked list, and then we're done for the whole semester. No more work.
That sounds exactly like Jimmy.
Yeah, he's so funny. He came in Halloween with a giant panda head. A panda head and like a nice suit on.
Really? Oh, that's awesome.
Yeah, so anyways.
You guys got any other questions for me?
Isn't a heap just like, kind of like, it's pointers as well?
Yeah. Yeah. So when you
But it
store
wouldn't
stuff-
be.
when you store stuff to
True.
the heap, it's not like the stack where there's like an order and you have it's like really efficient because you're using every bit of data, every address possible. The heap is kind of inefficient in the sense that you kind of you just randomly pick places. It's not actually random, but essentially you just randomly pick a spot somewhere in memory, and if there's enough space to allocate all the data you care about, it'll place it there. It's there in memory. Okay, but what if now? I guess I'll do a drawing. Stack stuff, other stuff. This is your heap. So let's say you allocate. Let's say that there's 100 units of memory there. So I'll say words. When I say word, that's enough space to store an instruction. If I store 60 words and I want to allocate it to the heap, it's just going to randomly pick like a swath of 60 words. So it could look like all of this. It could like all of this. It could be in the middle. Doesn't really matter. But it could be inefficient because what if I do put it right in the middle? Like this. Well, now there's only space for 20 word increments up and down at the bottom. And what if I just tried to place a 30 word set of data? Okay, well now you can't do anything because your heap's full. And so it's a little inefficient because if you had instead put it right at the top, now you have space for 40 contiguous data points. And now you can store that 30 word thing that you cared about. So it's not quite like a stack. It's not as efficient in terms of memory usage.
Wait, do we dynamically allocate things? Like, is that where the temp registers go?
Are you talking about high-level code or low, like assembly?
No, assembly.
You haven't done anything with the heap yet in assembly.
Yeah, I've seen it in diagrams, but I didn't know what we're like actually using it for.
Well, actually that's not true. You have used them. Every time you make an array, that's allocated to some space, probably the heap. Typically, in your C++ classes, you learn about dynamically allocated arrays. Those are also allocated to the heap. Statically allocated arrays, I don't believe those are allocated to the heap. I think they're allocated somewhere else. I don't remember where. Because they're static at compile time. But dynamic ones can vary in size, so they put them in the heap.
Wait, in Risk, though, you said when we do the arrays, like when we grab some random memory address for
When you do an array in Risk, yeah, I mean, you're just selecting somewhere in memory to put it. Well, the place that you put it in memory, it's not the stack. That's by the stack pointer, and it's not the program memory. It's not any of that stuff. It's somewhere in the middle. It's probably the heap, more than likely, because it's a pretty big area.
We don't ever have to like deallocate anything there. It's just like
Well, when you say deallocate, no, it doesn't go away. It's still there. It's just you stop caring about its values. So I say I have an array, and then I store useful information in there, and then I use the information for whatever I cared about, and then now the array is useless to me. In C++ code, you would either deallocate the array or you would just start ignoring the array. You just don't use it in your code. Okay, but that doesn't mean it's not there. It is still there. The actual data that you stored has not been changed by any other process up to this point. So the data is still there. You have just neglected it. You're not using it anymore.
Yeah, but you know how you get like memory leaks if like your object gets destroyed after the function?
So excellent point. Yeah. So when you do dynamically allocated stuff, you need to essentially remember where it's located and how big it is. And that's allocating space. You're not actually physically erasing the bits or anything like that. That's not what's happening. Your operating system is basically looking and saying, okay, I know this area, and that area are all occupied, and this area here and that area there are free. Again, when you deallocate something, all it's saying is my operating system is now going, okay, wait, I don't care about that area anymore. I can use it for new stuff. But the data that you just used is still there. It hasn't been erased. All you're going to do now is if you're going to put new data there, it's going to overwrite the old stuff. But it's still there until you start overwriting it.
So you don't get memory leaks in...
Well, you can get memory leaks. Those are a thing, right? Because what happens if you allocate this memory here, that memory there, and now all of your heap is filled up, now you're trying to allocate another thing. And your operating system's like, okay, I have used up all of the space I have. I simply do not have the space that you're trying to allocate. Oh, your program crashed. Sucks.
Mm-hmm.
That's a memory leak.
what is the error for that?
I don't remember. I don't know.
On my last job, like if we tried to do too many things, there was a very specific like SQL database error. Okay, so that's interesting.
Got any questions for me, Good Noodle?
I was thinking about what you said about memory leaks, and so like by continuously trying to allocate when you don't have any more space, that's like an overflow, right?
Typically, it's called an overflow in terms of the stack. So
Mhm.
the stack has bounds, and if you exceed the bounds of the stack by putting too much stuff on the stack, then you'll get a stack overflow. And there's a nice website also called Stack Overflow for that reason. But yeah, that's what overflow is. I don't remember what the error is called in terms of heap being allocated too much. It's a different. I don't think it's called overflow. It might be. I don't know. I don't remember. But yeah, it is for the stack.
I searched it up, and I think it says it's like heap overflow or heap overrun.
Yeah, that sounds right.
Oh, okay.
Yeah, if you ever look up coding questions, Stack Overflow is typically the website that pops up, and that is why it is named Stack Overflow.
Oh yeah. I don't know. I think like sometimes I really don't understand what they say on that website.
Yeah, it can be a little bit above your head. Yeah.
And like they like sometimes treat the questioner like they're stupid.
Well, of course
Like, I
not.
know.
How could you possibly think that? Yeah.
Can you take a breather in your sentence? Like, so I'm looking back at some of these like earlier Risk 5. They seemed so complicated at the time, but now they're
Now it's like, wow, this is kind of. I wish we were still doing this.
No, like translate if G is not equal to H, output G equals 0. I don't know. So I've gone through all the homework. Good Noodle, did you like? I don't know. Was there any risk stuff that you like wanted to go through, or like didn't?
I don't think so.
Yeah, I
How
don't
about you,
think
Shannon? Did you?
either.
Dr. Harris must be doing a really good job in class. You guys are getting a lot of practice with your homework.
Yeah. Yes, we are. Which is good.
Yes.
It's really good.
Hmm.
I mean, I know I'm probably going to ask you at a later date, like if we can review some of the different registers in System Verilog.
What do you mean, different registers?
Like synchronously resettable or an enable.
Oh, yeah,
Or
yeah.
like a enable flip flop or like just like those sorts of.
Enableable, resettable, settable,
Yes.
toggleable, flip flop.
Yes.
Yes.
Like when they start to get a little crazy and you've got like, yeah, the pausage clock or like the. I will definitely ask you to review one of those questions.
That works.
Like on homework 8, number 3. But maybe something like a little bit more complicated than that. Yeah, when we start like getting a whole bunch of stuff into
Okay.
the register.
Sounds good.
That's what so, but I'll definitely review over the weekend and then see like what's.
I do have a question on the term registers though. So
Yep.
when we're talking about registers, we were thinking more like on the flip flops when it came to like system Verilog, right? But then now when we're talking about registers in like RISC-V assembly, are those still the same registers or?
Registers are flip-flops. They are the same. The main distinction is, there are two main distinctions. The first is that you typically use the word register when you're thinking at a higher level of abstraction, whereas you use the word flip-flop when you're thinking at a lower level of abstraction. The second difference is, most often I've seen that if you have multiple flip-flops such that it creates a multi-bit flip-flop, that's called a register because it's multiple bits. So it looks something like this. Because physically, this is how you make a multi-bit register. You just chain a bunch of flip-flops, which all take in one bit individually and output one bit individually, and they're all connected to the same clock source. That's what a multi-bit register is. And if you have just one, I'll probably also call it either one, flip-flop or register, but typically you just call it a flip-flop. And if you have multiple chained together like this, typically you refer to the entire congregation as a register. However, you can use them pretty much interchangeably, and if you just mention the bit width, people will understand you. If you say a 1-bit register, they will know this is what you mean, because it is also a flip-flop. And if you say a 32-bit flip-flop, you'll probably get weird stares, but they'll understand you. They know you mean a 32-bit register.
So those are all being fed by the same clock, but they won't have the same clock value. So do you just like increase your?
They do have the same clock value. What do you mean?
Well, how can they, if they're all being fed from the same clock, but like they're at different areas of, like physical areas? Is
Oh
it
yeah,
like
there's a little bit of
not the
delay,
same
yeah.
amount? Yeah.
But if they're
delay.
close enough, the amount of delay is very negligible.
Okay.
Because we're talking like the signals being transmitted, not at the speed of light, but pretty darn close to it.
Oh, okay. And,
And
they're so
and
close.
since physically, because our technology's gotten so small, right, those things are nanometers apart from each other. So the signal races through in basically no time at all, and it's essentially no delay. That does, however, become a problem if you have stuff clear on the other side of your chip. That does become an issue, and so you have to deal with clock skew all across your chip, and you have to be able to correct that. Any other questions for me?
I think I'm done. Thank you.
Yeah, you're very welcome. All right, I'll go ahead and stop the recording then.